My name is Mohit, and I'm going to present a work on search-based task planning with learned skill effect models for lifelong robotic manipulation. The main motivation for our work is to be able to use robots for increasingly diverse tasks over time. For such diverse tasks, robots need to be able to learn skills over time and use these skills to plan efficient motions for these tasks. To do this, we propose a new approach in which we avoid any assumptions on the robot skills and incrementally learn effect models for newly added skills and use them directly for planning. Many previous works have proposed using skills for planning. Among them, most works focus on skills that can reach certain goal locations. That is, they assume each skill comes with a subgoal, while many other methods completely forego the subgoal assumption and hence fail to represent skills that require subgoals. In comparison, we support skills with arbitrary parameterizations, that is having both subgoal and non-subgoal parameters. We note that subgoal assumptions can be very restrictive, since it assumes skills will only have one desirable effect based on the subgoal parameters, while our approach can model multiple desired effects, each of which depends on the skill parameters in some way. We use these flexible skill representations and directly plan with them using search-based planning methods. We discuss our overall approach next. Search-based planning helps us find plans with our parameterized skills. This requires us to find the next node of the graph to expand. Given this node, we then need to find its successors, shown in the box below. To get successors, we simulate all skills that satisfy the preconditions and record the skill effects. To get these effects, we need to learn the skill effect model for each skill. Assume that we are given some trained task and some skills. As we run our planner from before, we get new data for each skill. This data contains the skill that was executed and its observed effects. We store all of the skill effect data and use it to train the skill effect model SEM using supervised learning. These skill effect models are now used to plan on any test task, which was never observed before. Over time, new trained tasks and new skills are added, and we use the previously learned skill effect models to plan on these new trained tasks, and we collect data for the newly added skills, which is again added to the skill effect data. We train the new skill models with this newly collected data and use them together with the previous effect models to plan on new test tasks. We use the tabletop manipulation domain to show the benefits of our approach. In this domain, we have a set of red and green blocks on the table. The goal is to put the red blocks into the far side of the yellow bin, which is not directly reachable by the robot. At start, we only have the pick and place skill. Since the task is infeasible with this skill, we get a very high execution cost shown on y-axis here. At the next step, we add the tray slide skill. Now the robot can put the blocks on the tray and then slide the tray over to the far side of the bin. Figure on the right shows that over time, as more data is collected, the learned SEM improves and the overall execution cost decreases. We now add the tray sweep skill. However, the skill does not provide any advantage to the existing skills, so the planner avoids using it, and as a result, the execution cost does not decrease. Finally, we add the bin tilt skill. Now the planner can use the tray sweep skill from previous step to put the blocks in the bin and then directly tilt the bin to complete the task, which leads to a reduced cost as seen in the figure. In conclusion, in this work, we propose an approach towards planning with a diverse set of skills and iteratively learning and planning skill effect models to solve tasks in a lifelong learning manner.